So the next thing we're going to talk about is adding and subtracting complex numbers. And so we do that just the same as when we add and subtract polynomials. So we're just looking for like terms. And so when I look at this, I'm looking for real number to real number. So 8 plus 5 is 13. And then imaginary to imaginary. So this is like a -1 in front. So if there's not a number, remember there's a 1. So -1i plus 4i, which would make positive 3i. And this is my solution. So again, real to real, so 7 minus 3, which is 4. And then you've got -6 minus a -6. So minusing a negative is adding. So -6 plus 6 is 0. If you like to do across the line, change the sign where you do change this to a plus problem and these to the opposites, you can do that as well if that makes it easier for you. But either way, there's not an imaginary part for this one. And so my answer is just going to be 4. For C, make sure you distribute that -1 to everything. So this is 13. Oops, that doesn't look like 13. So 13 minus 2 minus 7i, and then plus 5i. So we distribute the -1 first, or the negative sign, and then we're going to do the same thing. We're going to do the real parts. So 13 minus 2 is 11. And then you're going to do the imaginary part. So -7 plus 5 is -2i. And this is my solution. When we look at example 4, we're talking about solving a real life problem. So it talks about electrical circuit components, such as resistors, inductors, and capacitors, all oppose the flow of current. So it talks about the opposition is called resistance for resistors and the reactance for inductors and capacitors. So it says each of these quantities is measured in ohms. The symbol used for ohms is our little omega sign, which is an upside down, looks like an upside down U. It's a Greek letter. And they give us a table. So our resistor is capital R, our inductor is L, our capacitor is C. And the impedance, so that's for our reactance. For our impedance, resistor is R, inductor is Li, and capacitor is -Ci. So they tell us the relationship between the pieces. And the question is to find the impedance of the circuit. So as we look at it, we're just finding what our values are. So our capacitor for each of them, or the circuit that's going to be created, is going to be represented by the inductor of 3 ohms and the impedance of 3i. And then the capacitor has a reactance of 4 ohms and the impedance is -4i. So basically all we're going to do is combine the real and the imaginary parts. So as we look, our real parts are going to be our 3 plus 4, which is 7. And then our imaginary parts is the 3i and -4i, which is -i. And so the relationship or the impedance of the circuit would look something like this. If you look at the monitoring progress, same idea. I would pause the video, look at your answers, see how you do, and then get your answers and then come back and look to see if you're doing okay. So as we look at number 7, you've got 9 plus -6, which is 3, and you have -1 plus 7, which is 6i. Number 8, you've got a subtract 8, which is -5, and you have 7 minus a -2, which is the same thing as adding, so you get 9i. 9, you want to distribute, so you've got -4 minus 1 minus I, and then -5 minus 9i. And so as you combine regular numbers, you've got -4 minus 1, which is -5, and -5 minus 5 is -10. And then when you look at your imaginary, you've got -1 minus 9, which is -10i. And then with it being an addition problem, you don't really need to distribute anything. You can distribute the 1, but it doesn't really change what's in parentheses in this case. And so when we look at our real and imaginary, our real is 5 plus -9, which is -4, and then 3i plus 6i, which is 9i. And then in number 11, you're just going back to example 4. So it says, what's the impedance of the circuit when the capacitor is replaced with one having a reactance of 7? So as we look back up here, this reactance right here, they're saying if this 4 changed to 7 and the impedance changed to -7, because it's just going to be the opposite, then how is that going to change? And so it wants to know how that changes the value, okay, of the capacitor. So as we look, that's going to be exactly the same as what we did up above. So we're just going to do 3 plus 7, which makes 10. And then you're going to do 3i and then minus or plus -7i, which is going to be -4i. And then the next thing that we're going to do is talk about multiplying complex numbers. And when we multiply complex numbers, it's the same as what we did when we multiplied with binomials. So we're going to have a and bi in one spot and c and di in the other spot. And remember that these are variables. So when you multiply, they're just going to be multiplied together. So this is a times c. And this is going to be b times c times I. This is going to be a times d times I. And this is going to be b times d times I squared. And the reason why we talk about this is because of this I squared. That's the same thing as b times d times -1, which means this box ends up being negative b times d every single time. And so what happens is then I end up with like terms. So I have like terms on the diagonal. And so what you want to do is you just want to make sure that as you're looking at these, that you realize that that's what you have. And so as we look at this case, our like terms are diagonal from each other. And so when we look at, and I'm going to just change the color really quick. If we look at our diagonals in this case, we get our diagonals are here and our diagonals are here. And what we end up doing is we're going to combine those like terms, and that's going to always happen and work out really nice. And I like doing the box method. You can do distributive property, but I think the box method works the best. So if it's just one term, as I look at this one, as it's one term, I would just do distributive property like we normally do. So real times real. So 4 times -6 is -24. The I gets tagged on. And then there's really a 1 here. So 4 times 1 is 4. But then I times I is I squared. And when you see that I squared, that's the same thing as -1. So this is -24i plus 4. I squared is -1, which makes this term right here turn into -4. And then when it asks you to write it in standard form, that means you wanted to write it as a plus bi. So you want the real part first, and then you want the imaginary part. And so I'm just going to flip it around. And when you guys put that in the computer, make sure that you pay attention. It always wants it in standard form. So it wants the real part and then the imaginary part. When I look at B, the first thing I want to do is I want to draw myself a box. And I'm going to multiply. So I've got 9 and -2i. And then I have -4 and 7i. And then you're just going to multiply, just like we did before. So -4 times 9 is -36. And then -4 times -2 is 8 with an I. 7 times 9 is going to give us, 63 with an I. And 7 times -2 is -14 with an I squared. And again, I squared is the same thing as -1 every single time. So negative times a negative makes this box be not a positive 15. Negative times a negative is a positive. 14 times 1 is 14. And then when you go to combine like terms, these two on the diagonal are your like terms. And again, we're going to add every single time. So if I go -36 plus 14, So negative 36 plus 14 is going to give us negative 22. And if I go 63 plus 8, that's going to give me 71. And I'm going to do an I. And so this would be my answer. But the multiplying part is the same as we do with the normal box. So I would just pause the video for a minute, try 12, 13, and 14, and then come back and see how you did. So 12, you should have got negative 30i squared as your first step. And then remember, I squared is the same thing as negative 1. So this would give us positive 30. As we do distributive property, we have, this is really a 1 in front, so we get 8i minus I squared. And again, I squared is the same thing as negative 1. So this is 8i minus negative 1. Minusing a negative is the same thing as a positive. We don't have like terms, but we do need to rewrite it in standard form. So the real part, the 1's going to go in front, and the 8i is going to get put at the end. And then 14, I'm going to do 14 over here to the side. So again, our first step is to do the box. So this is 3 plus 1i, and this is 5 and negative 1i. And I just put the 1's in front just to help us. So 5 times 3 is 15. 5 times 1 is 5, and the I gets tagged on just as if it was an X. Negative 1 times 3 is negative 3. I gets tagged on. Negative 1 times 1 is negative 1. I times I is I squared. And again, I squared is the same thing as negative 1. So this ends up being negative 1 times negative 1, which makes this box really be a negative times a negative, which is a positive 1. And then just like before, these are our like terms on the diagonals, and we're adding just like we did before. So if I go 15 plus 1, then I'm going to get 16. Oops. And when I do negative 3 plus 5, I get 2i. And so this is my answer. And again, this is over here. Our next thing that we're going to talk about is our complex conjugates. And remember, when we did rationalizing the denominator, a conjugate was the same exact thing except for opposite signs. And it's the same thing that happens here. So if you multiply a number and its conjugate, so this is a and negative bi, notice what happens. A times a is a squared. A times bi is a times b times I. Negative b times a, or negative bi times a is negative a times b times I. And then negative b times positive b is negative b times I squared. And on the diagonals, well, a couple things. First off, notice that this I squared is the same thing as negative 1. So negative times a negative is a positive b. And then when you look at your diagonals like before, so we look at these diagonals, notice that as I add them together, I forgot to put a b squared here. So this is b squared. So negative 1, remember this is like a 1 and a 1. So negative 1 times 1 is negative 1. B times b is b squared. I times I is I squared. I just forgot the b squared part. So this little guy ends up being just a positive b squared. But when you combine the diagonals with each other, a squared plus b squared is going to stay a squared plus b squared. Okay, but now as you look at the diagonals going the other way, negative abi plus positive abi makes this term go away. And so you're just left with this whole idea of a squared plus b squared. And so it always ends up being a real number because those are, when you multiply a and b are real numbers, the I part goes away. So the nice thing about that is if I multiply 5 plus 2i and its conjugate, so its conjugate would be 5 minus 2i. So when I multiply them together, notice what happens. I'm going to go 5 times 5, which is 25. I go 5 times 10, which is 10i. Negative 2 times 5, which is negative 10i. Negative 2 times 2, which is negative 4. I times I is I squared. So the I squared is the same thing as negative 1. Negative 4 times negative 1 makes this box really be positive 4. And so what happens when we look at the diagonals again, and we're adding, so notice what happens when I combine those together. 25 plus 4 gives us 29. And then negative 10i plus 10i makes that go away. And so we're left with just 29. And so multiplying by the conjugate will always make a real number. Just like when we multiplied by the conjugate, it always made the denominator be a number instead of a radical. So as we look at the monitoring progress, same idea. Pause your video and then check these ones out. And if you need help, make sure you ask. So if I was looking at 15, the conjugate is 1 minus I. And so when I multiply in the box, it's the same idea. We have 1 plus 1i, and then 1 plus negative 1i. And so I can use the box, and I can always use the box. 1 times 1 is 1. 1 times 1 is 1i. Negative 1 times 1 is negative 1i. Negative 1 times 1 is negative 1i squared. This is negative 1 times negative 1, which makes this box be 1. And so now, again, when you look at that whole idea of our crisscross and we add them together, notice again how these ones go away, and we're really left with the a part, 1 times 1, and the b part squared. So remember that this is a plus bi. And so when we did the problem up above, we noticed that it was a squared plus b squared is our answer. If I take the a, which is 1, I take the b, which is 1, and I square them and add them together, I get 2, which is the same thing as if I added 1 plus 1 here, I get 2. So if this is a minus bi, so the opposite would be 4 plus 7i, that's the conjugate. If I do the box, I'm still going to get the same thing as if I just did a squared plus b squared. And again, this only works when you're multiplying a complex number by its conjugate. So a is 4, so this is 4 squared, and b is negative 7 squared. So this is 16, this is 49. When they add them together, I get 65. 17, the same idea. This is a, and this is b. The conjugate would be negative 3 plus 2i. So you're more than welcome to do the box because that's always going to work. Or you can just take the a value, square it, take the b value, square it, and add them together. So negative 3 squared is 9. 2 squared is 4. We add them together to get 13. And that's the easiest way to do that. I also want to just talk about really quick, if you have radicals with i's, we're still going to simplify the same way. And so I just want to go over just a couple examples here, just because you're going to see it on your homework, and I just want to make sure we're all on the same page. If this is 2, negative 2, and let's say this is plus 4 root negative 8, notice that I would simplify this the same way. We talk about the negative sign. This is negative 1 times 2. And this little guy here is the same thing as an I. So the I is going to go out. So this will be 2i root 2. If I look at negative 8, this is negative 1 times 8. 8 is going to break down to be 2 times 4. 4 breaks down to be 2 times 2. So as I'm looking at the 8 broke down, the 4 broke down. And this negative I is the same, or negative 1 is the same thing as an I. So there's already a 4 on the outside. The I is going to come out, and then you have a pair of 2s, regardless of how you take those pair. You can take the 2 there, you can take the 2 here. But a 2 is going to come out, and you're going to have a 2 left over. So when you get that, this is going to be the same thing as 8i root 2. And now we're back to that whole idea of this is a root 2 and this is a root 2. And both of these are imaginary parts, so I can combine them. 2i plus 8i is 10i root 2. And that's perfectly fine. As we simplify radicals, it's kind of like this, well, not kind of, it's exactly the same when we have roots. If you have the same value under the radical, then you can combine, but you always want to simplify first. And so nothing has changed. You simplify still the same. If this one didn't have a negative and this ends up being a 2i root 2 and an I root 2, then you can't combine them because you have an imaginary part and a real part. But if they both end up being imaginary, then you're more than welcome to combine the imaginary parts and the radicals like the variable part, just like before. So you're going to have some problems where you're going to have to simplify first and then combine like terms. And I just wanted to give you a heads up on that. And everything works out the same, but just be aware. All right, that's everything for 4.6. If you're struggling, make sure you ask for help. I'm available on Zoom. So either just jump on or email me and we'll schedule an appointment. So I will talk to you later. See ya.